Welcome back to another lecture from Organic Chemistry. In the last lecture, I actually initiated the discussion about infrared spectroscopy or IR. And before I go through this IR spectrum, I want to actually talk about what we are dealing with whenever we send light to a molecule. Okay, so remember, any molecule that you pick is made of electrons, protons, and neutrons. Okay, and it depends to the energy that you are applying. You can actually target electron. Okay, you can send electron from one layer to another layer, and it depends to the gap between them. We can call it electronic, vibrational, or rotational. Okay, let's start with this. Okay, we have one electron sitting in lower level of energy. Okay, let's call this one n equal 1. Okay, so first level of energy, and we're going to apply energy. And we're going to send this electron to, let's say, to this level. Or we can send this electron to the second level. Okay. Yellow line, the red line that they are highlighted yellow, okay, they are representing electronic shells, okay, or electronic layers. And I'm transferring electron between those layers. So this transition of electron from one layer to another layer, we call it electronic transition. And the technique that you are going to use here, it will be UV vis. Okay, because you will transferring electron from one layer to another shell. Okay, between two layers of level of energy, you have a bunch of vibrational. You have a bunch of vibrational actually layers. Okay, so those are going to be vibrational. Vibrational layers. Okay, so I'm gonna say, for example, I'm taking one electron, okay, and electron used to be here, and I'm sending that electron, let's say, to this layer, okay, and electron can go there, and of course, electron also it can relax from that layer to the second one, okay. And if you are transferring electron between vibrational layers, in that case, we say you're dealing with vibrational techniques, or in this mode or transition, you can call it vibrational transition technically. Okay, next, between two layers of let's say vibrational, you can find really small layers, some layers that the gap in energy between them is really small. Okay, if I zoom here, okay, the one that I highlighted pink, like orange, I highlighted the orange, they are okay, they're going to be rotational, okay? Rotational, okay. Layers, you can call them, and the technique it will be rotational, technically transition. Okay, so we have an electron, okay? Let's say we have an electron is here, and that electron, we're going to send it to, for example, there. Or electron, it can go there. Okay, and of course that electron it can relax, and it depends where it's going down. Okay, it will give you different wavelength. Okay, but that wavelength is going to be a range of microwave. Okay, this one it will be microwave range. Okay, so we use microwave waves to go after rotational transition. But if we want to talk about vibrational transition, the technique, the wavelength that you need to use, there will be infrared. Okay, and I said the previous one, they were UV vis. Okay, so let's summarize whatever we said. If you're transferring electron from first layer, okay, electronic layer, to the second electronic layer, we say you're dealing with an electronic transition. If you take it from if you are still between those two layers, between two electronic layers, you are not sending it to another higher electronic layer. Still, we're talking about one electronic layer. Okay, so we are between these two layers. We are not going out of those two layers. And the electron, we are sending it from one layer of electron, vibrational layer to another vibrational layer. Okay, and because the gap between them is less, the energy that you need to use, it will be less, and it will be in infrared range. Okay, next, you are dealing with layers between two vibrational layers. Okay, so the previous one was two electronic. Now we're talking about two vibrational, and between those two vibrational, we have a bunch of small, layers or level of energy, and those level of energy are in the range of microwave, and or you can say rotational transition. Okay, and the one I'm going to go after it will be this. So we are not transferring electron to another layer. It means we are not going to break any chemical bond. Okay, we are not going to change any chemical bond here. Okay, there the bond length is going to change because you are sending electron from maybe from bonding to anti-bonding, and that's going to change the bond length. There will be some shake with the bond length. Here, we are not touching. Okay, we are not touching actually the electrons we're not transferring them from, for example, bonding to anti-bonding. That's not going to happen. Okay. Now, let's get back to our slide. What do we have here? We have a spectrum in this IR spectrum. And what do we have on the left side? The left side is showing you how much of the wave that's past the molecule, okay, past the molecule, versus wave number. And what's a wave number? Wave number is equal to 1 over lambda. What was the unit of lambda? Okay, 1 over meter, or you can say 1 over centimeter. So you get 1 over centimeter, and that's going to be, forgive me, 1 over centimeter. You can call it centimeter to the power of -1. So, or meter to the power of -1. But because we are using it, we're talking about small objects, the centimeter to the power of -1 is good enough. Okay, now how do I read this? Okay, we have here, we have some wave numbers. Okay, and as you go to left side, the bond gets stronger. Bonds get stronger. That means in this range, they are weaker. Okay, the bonds are weaker, or you can say you need less energy to vibrate it. Okay, maybe I need to be careful about using weaker here. Okay, because okay, let's stay away from, forgive me, stay away from weaker for a second. Okay, I have a reason behind it. Okay, but as we move to the left side, we say the bonds are going to get stronger. You need to use higher energy to vibrate them. Okay, next, what's the meaning of this? This one is showing me. Okay, it's showing me that almost 90% of the light got absorbed. Only 10% of it, only 10% is passing. Okay, and how about here? If I connect this one to that line, okay, that's around, let's say 30. Okay, around 30. So it's telling me that 70% of the light that we send the molecule got absorbed, and only 30% of it is passing. You're reading the light that is passing the molecule, whatever passed. Okay, not the absorbed. Be careful, not the absorbed. Okay, and the range here is from 400 to 4,000 centimeters to the power of -1. Okay, couple of specs that you need to know them or be careful about them whenever you are using IR. Okay, first thing is, okay, we have a formula, and the formula says wave number. Okay, wave number is going to be equal to 1 over 2p c multiply. Okay, this you can say k or f divide by reduce mass. Okay, reduce mass. And what's the k? Is a constant number equal to f, and you can call it force a constant number. Okay, next. As the bond gets stronger, you need to apply a higher amount of energy to stretch it. Okay, like imagine you have a spring and you want to actually pull the spring. As you make the spring thicker, you need to apply higher force to pull it. Okay, to pull it or stretch it. Okay, as the mass difference. Okay, be careful. The mass difference between the two molecules, two atoms, gets bigger. You need to apply a higher energy to, again, higher frequency to vibrate that that bond. Okay, look to carbon and hydrogen. Okay, in order to stretch that one, we need to apply 3,000. Okay, wave number. And if we replace hydrogen with deuterium, which is heavier than hydrogen, this one goes down. Okay, and now replace hydrogen by oxygen. Clearly, oxygen is heavier than hydrogen and went down. And if you apply, like if you apply a carbon, you put chlorine instead of hydrogen, the drop is dramatical. Okay, and how about next one? Next one, it says a force, okay, or a K. Force constant or K. What's a force constant? Okay, if you attach two atoms through a triple bond versus single bond, those two atoms that they are in a triple bond, they will be closer to each other. And because they are too close to each other, it will be so hard to pull them far from each other. Or like, when you have a spring, and the spring is too small, okay, too small, but it's really thick, and you want to pull it, you need to apply higher energy, okay, higher energy to stretch it. Imagine that spring was stretch one, okay, longer one, and because it's longer one, when you pull it, you see like there is less resistance. So as the bond gets shorter, you have to apply higher energy to vibrate it, okay, or to technically stretch that bond. Okay. let me write some calculation for you so then you understand really what I'm talking about. Okay, so we have wave number is going to be equal to 1 over 2pc multiply, okay, we said force divide by m, reduce mass. And what's a reduced mass? Reduced mass is going to be equal to m1 multiply m2 divide by m1 plus m2. Okay, so imagine you have carbon attached to hydrogen. Carbon is 12, hydrogen is 1, the mass for them. So the reduced mass for it is going to be 12 multiply 1 divided by 12 plus 1. Okay, that's going to be 12 divided by 13. This number is going to be something around 19. Okay, let me do the calculation. So I have, sorry, it's going to be around 0.9. 12 divided by 13, so something around, okay, 0.92. Okay, how about this? Okay, let's replace it by carbon with oxygen. Okay, carbon with oxygen. The reduced mass is going to be 12 multiplied oxygen is 16. So you multiply it by 16 and you divide it by 12 plus 16. Okay, so in this case, I'm going to say denominator is going to be 28, numerator. Okay, let's see. We have 12 multiplied 16 divided by 28. Okay, number here I got, it says 6.86. Okay, so from 0.92, we jump to 6.86. Okay, let's go back and check the reduced mass. Where is the reduced mass? Reduced mass is inside the denominator. And what will happen if the denominator goes up? As the denominator goes up, the frequency number will go down. Okay, will go down. So you can say this. You can say wave number is inversely connected to, okay, inversely connected to the reduced mass. As reduced mass goes up, frequency, the wave number that you need to apply to, stretch or vibrate that bond, it will be less. So you're going to spend higher amount of energy to vibrate CH versus CO, okay, versus CO. Okay, and this is the reason that, for example, for CH, it depends with the hybridization, it can be around, for example, 3,000. Okay, well, this one, it can be around 12 to, okay, again, it depends what you're dealing with, 12 to 1,400. Okay, you can have CO, CO stretching, CO bond, stretch for CO bond. Okay, somebody might ask this, say, we have OH versus CH. Okay, and you said this, okay, you said wave number is equal to 1 over 2pc multiply force divided by reduced mass. Okay, and you might say electronegativity of oxygen higher than electronegativity of carbon. So I expect OH bond to be shorter than CH bond. Okay, then CH bond. And that's true. That's true. Okay, OH bond is shorter than CH bond. So that means the force for OH is higher than CH. Okay, so force for OH bond is higher than CH bond. Okay, than CH bond. But then you have to include this one also in your calculation. Okay, that's how about the reduced mass? Okay, how about this? Okay, I need to see effect of that one. Okay, so reduced mass for carbon for CH is 12 multiplied 1 plus divide by 12 plus 1. The reduced mass for OH is going to be 16 multiplied 1 divided by 16 plus 1. Okay, let's get the relationship between those. Okay, so we have 12 divided by 13. That's going to give us 0.92. And 16 divided by 17. Okay, this one is 94. Okay, so the reduced mass is working against, against actually the frequency here. Okay, reduced mass is telling us that CH should have higher frequency than OH, just the reduced mass. Okay, just the reduced mass. But then electronegativity or the bond length, it says OH. Okay, H is attached to oxygen, and because oxygen is more electronegative than CH, OH should be shorter than CH, and OH should show up in higher frequency than CH. Okay, true. Okay, true. But you keep this one in your mind that you have two factors that they are working against each other. Electronegativity is favoring OH, while reduced mass is favoring the CH. Which one is dominant? In this case, for OH, electronegativity. But you have to be careful about actually using this formula. Okay. Next, and here we have a chart that is showing us, like a range, and anything lower than 1500, okay, lower than 1500 is the area that sometimes we call it actually a fingerprint region. That one is showing you single bonds. Okay, between 16 to 1900, you're talking about double bonds. And if you have like a peak between 21 to 2300, that's a triple bond. And where are the H bonds, H attached to carbon, oxygen, whatever? Usually they show up around something around 29 or higher. Okay, 29 or higher. So from now, anytime you see like a spectrum, put line and separate. Okay, put line on 1500 and look for this region. Okay, this region, or the diagnostic region, is the region that is going to help you to characterize the functional group. Okay, and this one, the single bond, is going to be too crowded, and honestly, it will be so hard to use it for the purpose of characterization. And thank you very much.